Assalamualaikum and a very good day to my panel. My name is Nur Ain binti Arifin. Today, I would like to present about my final year project presentation. The title of my final year project presentation is Thermo-Hydraulic-Electrical Analysis of Hybrid Nanofluid Aluminium Oxide Silicon Dioxide Water in Pemfc Charge Channel. I am under supervision of Dr. Dr. Irni Azim Zakaria. For the introduction, proton exchange membrane fuel cell, also known as Pemfc, is one of type of fuel cell that generate electricity through electrochemical reaction between hydrogen and oxygen. The Pemfc produce heat and water as byproducts. Pemfc is one of the greener option to the fossil fuels since the emission is almost negligible. Pemfc can be used in all applications such as automotive, industrial, and aircraft. Nanofluid is nanoparticles suspended in base fluid such as water, ethylene glycol, bioglycol, and etc. The nanoparticles can be categorized into four main groups that are metal-based, metal oxide-based, carbon-based, and hybrid or mixed metal-based. The advantage of using nanofluids in Pemfc is that it is one of alternative way of cooling method without sacrificing the radiator size in Pemfc. This research is about the effect of heat transfer, pressure drop, and electric current drop by hybrid nanofluids, aluminum oxide, silicon dioxide in water in Pemfc charge channel. The objective of my research study are focusing two main things. First, to study the effect of hybrid nanofluids in terms of heat transfer and pressure drop in charge channel of Pemfc. And second, to investigate the electric current drop in charge channel of Pemfc due to nanofluids. The scope of study of my research study are divided into four studies. First, proton exchange membrane fuel cell, to be specific, charge channel. The second one is properties of nanofluids, which are aluminum oxide, silicon dioxide, and water. Third, Reynolds number varies from 300 to 700. Lastly, the heat transfer, pressure drop, and electric current drop. For the methodology part, I need to know how to calculate the mass and volume of nanofluids, which are aluminum oxide and silicon dioxide respectively. These are two formulas that I have been using to calculate the nanoparticle mass and volume. The phi symbol represents the percentage volume of concentration. For my research study, only 0.5% volume concentration of nanoparticles required. The method used to prepare the nanofluid is two-step method. The method only involves with stirring and sonicate. The duration for stirring require about 20 to 30 minutes of stirring. Meanwhile, the silicon dioxide required 10 minutes to completely disperse in the base fluid. For sonication process, the process duration required 3 hours for both nanofluids. This is due to increase the stability of the nanofluids. For project finding, first is the channel temperature. The figure below shows the Reynolds number increase as the channel temperature decrease. The lower the channel temperature, the indicates better heat transfer of the fluid. The highest temperature drop observed at Reynolds number 700, which is 1090 of aluminum oxide silicon dioxide with 3.34% increment as compared to the base fluid water. This temperature reduction is due to the improvement of the thermal conductivity properties of the nanofluids. Higher thermal conductivity will result in higher Brownian motion movement that will improve the heat transfer behavior of the fluid. The next is heat transfer coefficient. The heat transfer coefficient defines the convective heat transfer ability of a moving fluid. The higher the value of the convective heat transfer coefficient shows better heat transfer capability. Based on the figure, the highest transfer coefficient was 0.5% volume concentration of aluminium oxide at Reynolds number 700, which was 43.12% higher than the base rate. The next is Nusselt number. As Reynolds number increased, the Nusselt number also increased based on the graph. A non-dimensionalized Nusselt number value was calculated from the convective heat transfer. Highest Nusselt number given by singles aluminium oxide due to the significant effect of convective heat transfer as compared to the convective heat transfer. The hybrid nanofluid have lower value of thermal conductivity compared to single nanofluids of aluminum oxide and silicon dioxide. The next is pressure drop. As Reynolds number increased, the pressure drop also increased. The highest pressure drop was recorded at 1090 ratio of aluminum oxide silicon dioxide hybrid nanofluid, which was 7.226 Pascal, which is equivalent to 63.71% increment as compared to the base fluid of water. The 0.5 of volume concentration of aluminium oxide was recorded as the second highest, which was 6.227 Pascal, equivalent to 63.41% as compared to the base fluid. The pressure drop show higher increment on hybrid nanofluid compared to the single nanofluid. This is due to hybrid nanofluid possess higher density and viscosity compared to the single nanofluid. The pumping power increase as Reynolds number increase. This is due to higher density and higher viscosity of the nanofluids. The highest pumping power was recorded at Reynolds number 700 for 0.5 volume concentration of aluminium oxide. And lastly, the current drop. The pattern showed that as Reynolds number increased, the current drop also increased. The highest current drop was recorded at Reynolds number 700 for singles aluminium oxide. This is due to more conductive current flowing, thus more current drop recorded. I think that's all for me. Thank you. And if you have any inquiries, you can contact me to the phone and email stated at the slide. Thank you.